Now, one of the things we know is about the binomial distribution. So let's go back to that. So three things we can say about it. It applies to Bernoulli trials, so independent trials all having the same success probability. And these are just yes-no trials. Pass, fail. They either succeed or they don't. And the binomial distribution applies to the random variable that counts the number of successes. When we do n trials. Well, today we're going to consider changing one or two of these features. Instead of just yes-no trials, we could be a little more flexible. We could have three-way trials. The heads, tails, or stand on edge. Four-way, five-way trials. Or we could change the random variable. Instead of counting the number of successes, we could count something else, namely how many trials you need to get that first success. Perhaps the probability of success is very low, and we're interested in how many trials we expect to need to get our first success. Well, first let's try changing from yes-no trials to three-way. First, let's, for the binomial distribution, let me write down again the formula for the probability mass function. Well, the formula you know. It involves, first of all, the number of ways to arrange those k successes. Yes, k yeses and n minus k nos. Times the probability of each such outcome is they all have the same regardless of the order in which we scramble these letters. A yes has probability p, a no has the opposite probability. Well, old hat. That was binomial. What should trinomial be? Well, it should be just the same except for one thing. Instead of bi, it's tri. Okay, so say we have these independent trials. But each one, yeah, it could be heads or tails or stand on edge. It has three options. So say option 1 happens with probability p1. Option 2, option 3. And these have to add up to 1. And we might want to count the number of trials that come up heads and the number that come up tails and the number that stands on edge. Let's work a problem. You have this pill, and it's not perfect, and you give it to a bunch of patients, where a bunch means 8 of them. And presumably the patients are independent of one another. What happens to the first patient won't affect the second one. The pill works half the time. It has no effect at all a third of the time. And unfortunately, has a harmful effect the rest of the time. Well, so that has to be 1/6. Adds up to 1. So we give the pill to 8 patients. And presumably the patients are all independent. And we might want to find the probability of, say, that it works for 4 of the patients, has no effect for 3 of them, harmful for 1 of them. Of course, these numbers have to add up to 8. Well, let's work this problem. The same way we did for binomial. How many outcomes are there? 4 of this kind, 3 of this kind, 1 of this kind. And what's the probability of each one? Well, probability that we'll get this 4-3-1 pattern. Well, there are a bunch of outcomes that give us this 4-3-1 pattern, namely the different orderings, number of ways to arrange. We want it to work for 4 of them, no effect for 3, and harmful for 1. These 8 letters. Well, but that's old hat. We know how to count the number of ways to arrange these 8 letters. We did that back in section 12.1. 8 factorial over 4 factorial, 3 factorial, 1 factorial. And then we multiply this by the probability of each one. This tells us how many outcomes there are with the 4-3-1 pattern. Times the probability of each. Same as for binomial, except now there's 3 options. Well, the pill works half the time. So to get these 4 successes here, so a half times a half times a half times a half. 4 of them. And we just multiply them because the patients are independent. For the 3 no effects, that's 1/3 times 1/3 times 1/3 times 1/6 to the 1. Well, so when we work this out, well, that counting part is not too bad. 8 times 7 times 6 times 5, and then some things that cancel with the 4 factorial, divided by 3 factorial, which is 6, and 1 factorial is just 1, so we'll ignore it. The 6's cancel. 40 times 7. There are 280 of these, but then we have to multiply by this probability, and for that we pretty much need a calculator, so I did this ahead of time, and we get the probability of a 431 result. Well, to 3 figures, it's 10.8%. Like binomial, only it's trinomial. Well, more generally, what can we take away from this problem that will be useful in other trinomial distribution problems? Well, we expect to have these 3 probabilities that add up to 1. We're interested in an account that adds up to the number of trials, and we want the probability mass function. So let's write that down. Instead of 8 patients, say we have n independent trials. With 3 options. Well, we'll want to generalize it further in a minute. What if there's 4 options? Well, first let's stick with 3. So these 3 options have their probabilities. Option 1 has probability P1, P2, P3. And then we want the probability of getting, well, something like a 431, or K1, K2, K3. The probability that we get K1 of these trials that give us the first option K1 of the first kind and K2 of the second kind and K3 of the third kind is? Well, it's like this. We count the number of arrangements. To find out how many outcomes have this K1, K2, K3 count. So we know how to do that from section 12.1. There are this many ways to arrange those n letters, where K1 of the letters are the first are A's, and the K2 of them are B's, and K3 of them are C's. And then we multiply that by the probability of each one. They're all the same. P1 to the k1 power, p2 to the k2, p3 to the k3. Where these things add up, right? The probabilities have to sum to 1, and the individual counts have to add up to n. Well, it's what we did here. We wanted a more general statement. And this is called the trinomial distribution. And what if we want to go one step further? Maybe instead of 3 options, there's some other number. Well, so we'll call that multinomial. Where we have n independent trials and some number of options with their probabilities that add up to 1. And we use this same formula with the obvious changes. The same formula, mutatis mutandis. Can I get away with that? It's Latin. Right, if we had 4 options, well, there's going to be a 4th term here. And here we're going to count the number of ways of arranging those n Scrabble tiles where there are 4 letters represented. Let's work a problem. Okay, you have some coins in your pocket. There are 4 pennies, 3 dimes, 5 quarters. Okay, we're going to, some number of times, select a coin and replace it. So now, since it's with replacement, so the trials will all have the same success probabilities. And the number of trials is going to be 4. So 4 times. You select a coin at random from your pocket. You look to see what it is. And then you replace it. Well, so there's 12 coins altogether. We know how likely it is that you'll choose a penny. Here's the question. What's the probability of 61 cents? That is, you're selecting these 4 coins. Add them up. What are they worth? Maybe 61 cents. That could happen. How? To get 61 cents out of 4 coins, 2 of them have got to be quarters. If 1 or less is a quarter, you're not going to get enough money to get to 61 cents. You'll have to have 2 quarters, 50 cents, and the other 11 cents will have to be a penny and a dime. That's the only way to get 11 cents. So the only way to get 61 cents is to get 2 quarters, 1 penny, and 1 dime in some order or another. Well, so we've got these 4 independent trials, each with 3 options. And we want the probability that we get 2 of them coming out to be quarters, 1 penny, 1 dime. And we know how to do it. So let's try putting in the numbers. The probability that we get 2 quarters, the number of pennies has to be 1, the number of dimes has to be 1. Well, so first we count the number of ways to arrange these 4 letters. Well, we know how to do that from way back when. 4 factorial over 2 factorial, 1 factorial, 1 factorial. The number of ways to scramble those letters. And now we want the probability of getting any one of these arrangements. Well, so we need probabilities. There are 4 of these 12 coins or pennies. So we have probability 1/3 of getting a penny. 3 of the 12 are dimes, so we know the probability there. 5 of the 12 are quarters. So we have 5/12 squared for the 2 quarters times 1/4 times 1/3. Well, that's not too bad to work out. 4 factorial is 24 divided by 2. Okay, 5/12 squared. Well, some things cancel here. (25 over 144). As a fraction, we get this probability. It, as a decimal, to get a better idea of sort of how big this is, to 3 places it's 0.174. But what about the other change in this picture? Let's go back to keeping simple yes, no, pass, not pass, succeed, fail trials. But instead of counting the number of successes, we're going to count something else. Namely, the number of trials until you first succeed. Well, you might be lucky. Maybe it's just 1 trial, instant success. Yeah, and maybe not. So we want to look at the waiting time. So the new random variable we'll call W for waiting. It's the number of trials until the first success. So these are going to be Bernoulli trials for now. So they're independent yes, no trials each with the same success probability p. The usual setup for the binomial distribution, only now what we're counting is how many trials till we get our first success. After the first success, maybe we're going to stop. So if the smallest that can be is 1, if the first trial succeeds, then we can stop right away. It's 3 if we get failure, failure, success. No, no, yes. Well, let's find the probability mass function. Well, for some of the other problems we've done recently, we had random variables with a finite range, and finding the probability mass function just amounted to filling some numbers into a table. Yeah, but now we really want an algebraic formula, because the waiting time has infinitely many possibilities. The range of this random variable, well, the smallest it could be is 1, as I said. Or it could be 2 or 3 or anything. Right? If your luck is really bad, it could take millions of trials to get that first success. It is even conceivable that you never get a success, but extremely unlikely. In fact, probability 0 for p between 0 and 1. So we'll want to, we can't just make a table for numbers. We want an algebraic way of figuring out the probability mass function. So nonetheless, let's start off with the first few entries to see what the algebraic expression is going to look like. Each trial has success probability p, so the probability that w is 1 is just the probability that that first trial succeeds. Bang, and then we're done. The probability that w is 2. Well, for w to be 2, that means the first trial fails, and we know the probability for that. 1 minus p. And the second one succeeds, and the trials are independent, so we just multiply. So this is going to be the probability that the waiting time is 2. For 3, well, that means we had those 2 failures and then a success. Well, you see how it's going to go. Okay, so now we'll move the boards around and write it down. The probability that w equals k. That our first success is on the kth trial. So the first k minus 1 trials all failed. So 1 minus p to the k minus 1 power, and then a success. So this formula gives us the probability mass function for the waiting time. And a random variable with this probability mass function is said to have the geometric distribution. Now, I ask, what's geometric about it? Well, we'll put that off till next week. With this probability mass function, well, terminology is said to have the geometric distribution. With parameter p. And the times when we apply the geometric distribution is when we want the waiting time for Bernoulli trials. Well, you'll notice we're starting to collect an assortment of distributions so that we can choose the right one for each problem we come across, the binomial distribution, and then stretch slightly to multinomial. Now the geometric distribution, and there's going to be a bunch more. Okay, let's assume there's some high-risk operation, some high-risk procedure. That's fatal 10% of the time. Well, that sounds pretty bad, but it's a convenient number to work with. And of course, the cases are independent. As far as it's reasonable to assume the cases are independent, so let's assume that. So if we perform this procedure every now and then, we know how to, we could ask, what's the probability that the first fatality occurs with the 8th patient? Well, we have this formula for doing this. Means that the first fatality for the 8th patient, that means the first 7 were not fatal. So that's 90% to the 7th power. And then on the 8th, what it had was fatal. If we work this out numerically, that's about 4.8%. Well, one more question. What's the probability that the first fatality is later than this, sometime after the 8th patient? Well, the hard way to do this would be to say, well, if it's happening after the 8th patient, that means it's with the 9th or the 10th or the something later. So we could figure out the probability that it's the 9th, and the probability that it's the 10th, and the probability that it's the 11th, and so forth and so on, and add them up. Well, that means summing an infinite series, which is not out of the question, and which we will have to do on Monday anyhow. We'll have to look, in order to get the expected value for the geometric distribution, we'll have to sum an infinite series. But we don't have to do it right here and now, because there's an easy way. We're looking for the probability that the waiting time is more than 8. Well, that just means that there was no fatality in the first 8 cases. And the cases are independent, and the probability of no fatality would be 90%, and we want that to happen 8 times in a row. And they're independent. Well, this is about 43% numerically. And the probability that part C, probability that the first fatality occurs somewhere within the first 8. Well, that's the complement of this event. So that has probability like 57%. First fatality somewhere in the first 8. So in symbols, means the waiting time is 8 or less. Somewhere in those first 8. We had the first fatality. Well, so we could work that out by adding the probability that W is 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 and adding them up. Or we could take the shortcut. This is the complement of saying that W is more than 8. It's the complement of saying this inequality doesn't hold. And we just did that. It's 1 minus 0.9 to the 8, so that must be like 57%. Well, let's generalize these a little for later use. For the geometric distribution with parameter p, let's write down once again the probability mass function. Probability that W is k, well, just want to write it down again. Probability the first success is on the kth trial means we have some number of failures. The probability that the first success is later than that means the first k trials all failed. 1 minus p to the k. And for the cumulative distribution, the probability that W is k or less, well, that's the complement of the preceding event. So it's going to be 1 minus p to the k. Well, so these are the, oops. This was part B of the problem, this was part C of the problem, and the methods generalize. Well, there's a lot of things haven't said, like what's the expected value? If W has a geometric distribution, we want to know what its mean is. We want to know what its standard deviation is. Yeah, well, good questions, but we're not going to do it right now.